Do you know why the sky gets red at sunrise or sunset? How many people know? How many people really know? This is what somebody might tell you. Sunlight encounters more air molecules when the sun is lower in the sky than when the sun is overhead. Even more blue light is scattered away, leaving mostly the reddish component of white sunlight to travel the straighter path to your eyes, so the setting looks red. Sounds good, right? Yeah. Yeah, sure. But it's not the correct answer. What I'd like to do is demonstrate. So here's a nice, beautiful sunrise, a reddish sky. Let's look at glass dispersion and colors. You've seen this image before. White light passes through a glass and it gets dispersed into the spectrum. Red is the least refracted color. Violet is the most refracted. Keep that in mind. Red is the least refracted color. Alright? Concave Earth, glass sky, sunlight. Alright, let me try drawing this for you on paper. I gotta adjust my camera, but we'll see how we can do it. I gotta turn the camera upside down. 1 second here, guys. Alright. There's a camera. There we go. Alright. Sorry about the angle. That's the best I can do with this setting. Okay. Uh-oh. Get some more tape. There we go. Stay. Alright. Put the microphone over here. Okay. My trusty pencil. Now keep in mind this would be a full circle looking top down, of course. How does that work so far? Yeah, I just need a little glass sky. Alright. Okay, this is exaggerated, okay? But this would be 100 kilometers. So, move it up a little bit there. Sorry about that. So, you are here. And as I told you, the sun is moving within this space. This would be considered outer space, but it's really inner space. This is the celestial sphere. This is a glass container as well. This is the glass sky at 100 kilometers that was formed after the flood. And sunlight is bending within the earth, and the sun is only a half sphere. Alright? So it's bending. If this is the east and this is the west, the sunlight is bending around like that and hitting your eye. Okay? It's bending less severe when you're closer to the sun. When it goes through this glass sky, it gets dispersed, just like going through the prism, right, guys? The white light is going through here, and the red light is the amount that's least refracted, right? So you have the blue light, it's going to be, or the violet light is going to be more refracted. Okay? So you're not picking up the blues, all the other colors refract too much for you to see them at that angle, at this angle of incidence. You should study Snell's law a little bit to understand how that works. So the red, because it does not refract that much, is what you pick up the most. That is the true answer. Why the sky is red. Isn't it wonderful to know the truth? Oh, let's talk about, somebody brought up a question on my YouTube about megacry meteors, and a simple fact that, excuse me, the simple fact that when we look at megacry meteors, they're opaque. What's going on there? Let's find some pictures of megacry meteors. Look at that, they're opaque. This one fell on the Mustang. Remember that one in Florida? So how can an opaque glass be covering, or I'm sorry, an opaque ice be covering up the glass sky? How does the sunlight penetrate through? It's got to be transparent, right? Yes, it does. And it is. However, it's just not transparent at ground level. Because, let's go over here to temperature. There are two different states of ice, amorphous and crystalline. Amorphous means it's clear, transparent, like glass, and crystalline means it has structures, it has crystal structures, and it is usually opaque or very near opaque, translucent opaque. Okay? Keep that in mind. Let's go to that one reply I just made to this guy. At 100 kilometers, stop. At 100 kilometers, guys, or thereabouts, where the glass sky is and where the ice is attached to the glass sky, it is clear and it is very cold, and that's where the ice stays in the amorphous state. I just got these figures from Wiki, and I'll just read it to you. At 100 kilometers, you are just over the mesosphere, mesopause. This is where the temperature of the ice is cold enough to stay in the amorphous state. In the mesosphere, temperature decreases with increasing height. The upper boundary of the mesosphere is the mesopause, which can be the coldest naturally occurring place in Earth, with temperatures below 130 Kelvin, which is minus 226 Fahrenheit, or minus 143 Celsius. So it can be below that. It can be colder than these temperatures here. So there's a transition. Ice can go from state to state. Indiana to Illinois. No. It can go from amorphous to crystalline, okay? Based upon the temperature. In general, amorphous ice can form below minus 130 K. At this temperature, water molecules are unable to form the crystalline structure commonly found on Earth. Amorphous ice may also form in the coldest regions of the Earth's atmosphere, the summer polar mesosphere, where noctilucent clouds exist. That's actually volcanic ash remnants, but I'm sure there's ice there too. These low temperatures are readily achieved in astrophysical environments such as molecular clouds, circumstellar disks. Okay. An additional factor in determining the structure of water ice is deposition rate. Even if it is cold enough to form amorphous ice, crystalline ice will form if the flux of water vapor onto the substrate is less than a temperature-dependent critical flux. This factor is important. Okay, blah, blah, blah. At temperatures less than 77 K, irradiation. Okay, so at that level, the temperatures are cold enough to stay clear. The ice stays clear. But once it starts getting warmer, that ice gets opaque. So that's why. Okay? Originally, I didn't know this. I mean, I was just, okay, well, maybe it's opaque up there. But, once you start doing a little bit more investigation and, the questions start pouring in. But everything just falls right into place when you have that glass sky as your foundation of understanding. Isn't that great? We figured out the lunar waves, the linear polarization. We figured out where tektites come from. We figured out where megacryometeors come from. We figured out where the Libyan desert glass comes from. It's amazing. That's great. So there's my little graphic that I had made a long time ago. Okay, guys, it doesn't come from airplanes, doesn't come from windshield, doesn't come from water, doesn't come from Alaska. I sound like a broken record, I'm sorry, but just trying to help you guys understand. And, for me too, it's a process for me to comprehend what's going on too. So, it's the Lord Stephen Christ Discovery Project. Okay. That's enough for now. Bye. I gotta scratch my head. I just don't understand. I mean, the lie goes so deep, guys. Okay. You realize there's no spin to the earth. And so, their explanation as to why they say the hurricanes move in one specific direction north of the equator versus the opposite direction south of the equator is due to the Coriolis effect. No, guys, no. Here, let's just watch a little bit of this video.
The plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So, what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course.
See, they have to explain why, according to the Coriolis effect, it would be deflecting toward the right in the northern hemisphere. Yet we have the hurricanes going counterclockwise in the northern hemisphere, so they have to make up this bullshit explanation. Watch.
In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right.
Slightly to the left. No, that's not what's happening, lady.
The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye. Okay, stop right there. Okay, let me just go back here. Remember the fluid dynamics demonstration that I showed you before, where the guy was dropping dye into a still tub of water, of liquid, and he's not moving it, and he just flipped this little flap here, and it caused the same vortice that we see in the hurricane. Remember that, guys? I showed you that. So, I'll show it again.
And some orange food coloring. We're going to flip a little plastic flap there on the left side of the tank, right there, right at 9 p.m. There's the flap being flipped. That builds a vortex. We'll now speed up the speed of the movie so we can see it. And you can see it's strongly three-dimensional. There's tons of turbulence inside there, and it's quickly mixing together all the different colors. And that kind of a strongly three-dimensional, highly turbulent vortex is somewhat comparable to what you see in a hurricane.
Okay. There's no Coriolis effect going on over here, guys, right? And it's the exact same pattern as a hurricane. So what's going on? Well, let's look back. What do we see here? Okay, got my dry eraser. We see this vortex happening right here, right? See that right there? Bam. So you have a higher velocity around the perimeter there. So there's more force, right? There's more force toward the bottom end of this little vortice here as opposed to the top end. So it's spinning counterclockwise like that, right? Let's go on here a little bit.
That builds a vortex. We'll now speed up the speed of the movie so we can see it. And you can see it's strongly three-dimensional.
Well, simply if you flip the flap in the other direction, the vortice would spin clockwise, right? Like if you flipped it from the bottom up. So it's a variance in the velocity from top to bottom or side to side or whatever edge is exerting more force than the other edge, right? So now if we can look at our concave Earth, we realize that the sun is moving, right? Here's the sun. It's moving along. Okay, it's kind of nudging. So when we see hurricanes going from east to west, the sun is like nudging it along like that. Even in the southern hemisphere, the sun is nudging along the cyclone. They call them cyclones in the southern hemisphere, from east to west, just like how our sun moves. Okay, so now just simply look and understand. Within the Earth, it's warmer at the equator, right? It's hot at the equator and it cools off gradually the farther away you get from the equator. Now, if you understand anything about barometric pressure, atmospheric pressure, there's more pressure when there's colder air. There's less pressure when there's hotter air, when there's warmer air, okay? So, looking at a hurricane, let's go to Photoshop here. Okay, you look at a hurricane, the higher velocity is going to be north of the hurricane, on the northern edge of the hurricane. So there's going to be more force, more acceleration going on, more pressure. So it's nudging it along, it's going across the top, bam, like that. It's just like that flap, it's flipping it. The sun is moving across, it's nudging it along, but the flap, there's more pressure on the northern end of the hurricane in the northern hemisphere. That's why it is circling counterclockwise. We got the 6 and the 9. Remember, when it's counterclockwise in the north, just remember 6 and 9, 6 and 9. Okay, and then you go to the south. I got a little graphic here of the south. It's the opposite. Okay, the warmer air with lower pressure, lower speed is in the north now. And the higher pressure, the colder air, and the more velocity is in the south. So now it's going this way, the hurricane. Even though the sun is still nudging it along this way, for the most part, the hurricane is still moving from east to west. But the spin action is because there's more pressure in the colder region, on the colder side of the cyclone. We call them hurricanes in the north and cyclones in the south. But it's the same concept, okay? Has nothing to do with the Coriolis effect, guys. Okay? Pass this around, tell the whole world, okay? A spinning Earth is bullshit, okay? Hurricane-like vortices do not happen within a spinning container, let alone on a convex spinning ball, which magically holds water together to the surface by this magical force called gravity. On and on and on. Okay, you're inside the concave spherical Earth, okay, and ether is pushing you to the ground. There's a Coriolis force coming from the center. There's my other. But it's ether. It's an ether Coriolis force. I'll show you. See? Got this spin, but it's an ether Coriolis force. That's why when you shoot a bullet to the east, it will sink, and when you shoot it to the west, it will rise. I'm sorry, switch that. When you shoot a bullet to the west, it will sink, and when you shoot a bullet to the east, it will rise slightly. Okay, guys? There. Solved. What else can I tell you? It's solved. Ether, okay? This guy says it's all because of the spinning Earth. No, it's not because of the spinning Earth. You know, why is there a differential with the bullets? Okay, you got them going 8 inches lower toward the west and only 3 inches higher toward the east. It's because it's not a spinning Earth. Otherwise, it would be equal. It would be like 5.5 inches each way. But it's not. It's not. It's just simply the higher pressure, the higher speed. Higher pressure, colder temperature, higher speed. That is the direction. That is a churning, okay? This is in the south. This is in the north. You got the higher pressure in the north, in the northern hemisphere. You got the higher pressure in the north of the hurricane. And so that's where the velocity, where the momentum is going. It's pushing. That's where the flap is coming from. It's all right there, guys. What else can I tell you? Pathetic. 222,659 views. And it's Nova PVS. Later. Hi guys, I want to talk about atmospheric refraction and the conventional explanation of why atmospheric refraction does not work on a convex ball, planet Earth. There is a little bit of problem here with what they explain to you why atmospheric refraction is working. They will say it actually, warm air will bend up away from you, and that's actually what is happening, where it's bending up away from us. The sunlight, the air, it's bending up away from us, and therefore it is refracting, and it's also aided by a glass sky, but they don't say that. But this is their standard definition, explanation. Let me get a screen cap.
The ray of light will reach the observer at O, as if it had come in the direction AO instead of in its true direction BO. Consequently, we do not see the true position of the sun. It is due to atmospheric refraction that the sun is visible before actual sunrise and after actual sunset. Do you know this fact? The sun appears to rise 2 minutes before the actual rise, and it continues to be seen 2 minutes after it has actually set.
Okay, stop right there. This guy's saying that the sun appears to rise 2 minutes before the actual rise and continues to be seen 2 minutes after it has actually set. On a convex planet with the warm air bending up away from you, not toward you, this is in direct violation of what they say is happening here, okay? It should not be bending down toward the Earth. It should be bending up away from the Earth. So what I did is just simulated here in Lightwave a little test to show you what would happen if the refraction were happening on a convex planet. And basically what I do is I just added a little glass sphere over the convex Earth, and then I compared the two, and you're gonna get, let me get this up here. Okay, on the left side you see the sun rising without refraction on a convex planet, and on the right side you see the refraction happening because I turned it on. So it's the same. I mean, the angle of the sun is actually the exact same. It's not, the geometry has not changed. It's just the refraction added. That's the difference. So if I press play there, you see that the sun is rising slower on the right with the side with refraction. Therefore, on a convex planet with light bending up away from the observer, this would not. This would be what would happen. What would be happening? So the sun would be late, basically. See, if you look at the blue on the bottom here, it's the same value, even though the height of the sun is different. So basically, what would be happening if we were on a convex planet and there were refraction happening? The sun would be slower, and we would experience sunrise before we actually saw the sun, not after, like they say. They say that we experience sunrise after we see the sun, but it's the actual opposite. You understand what I'm saying? So, the truth of the matter is, that we're inside the concave Earth, and light is definitely bending. There is refraction going on, and the main reason why we see the sun before we actually experience sunrise is because of the refraction going the other way, and it also is aided, I believe, by the glass sky. If you watch this little video here I did before, you see how the sun rises like that inside a concave glass sphere. So it's rising, okay, plus the bending light. So that is really why we see the sun before we actually experience sunrise. It's the exact opposite. They totally contradict themselves. Thanks for watching.
In this cave, I am the king.